right, I think we're going to get started. So welcome everybody. This is the 4 Storms seminar series. I hope folks on the webcast can hear. For first, a few announcements. If there is an emergency, exit out the back doors, down the stairs, out the front door, and our meeting place is in Cesar Chavez Park. Restrooms are out the back, to the left, down the hallway. You should be able to find them there. This presentation is being recorded, and it will be posted on our Storms. Oh, I should advance the slides. It will be posted on our Storms page at waterboards.ca.gov/storms for later viewing. We will have a question and answer session after the presentation. For those on the webcast, please email your questions to storms@waterboard.ca.gov, and we'll try to answer them in a timely manner. For those in the room, please wait for a mic. We want to be able to capture it for those on the web and for the recording afterwards. All right, let's move on. My name is Matthew Fries, and I work for the Stormwater Planning Unit. We have the privilege of implementing the State Water Board's Stormwater Strategy, or as we like to refer to it, STORMS. The mission of the strategy to optimize resource management of stormwater is to advance the perspective that stormwater is a resource. These Storm seminar series are an open forum that feature new research, technologies, policies, and news relating to stormwater. And here to present on dry wells is James Mayer.
Okay. Can everybody hear me? Yeah? Okay, good. So, thank you, Matthew. Appreciate it. It was great to meet you guys a couple months ago with Annalisa, and we'd love to have this opportunity to talk to you about dry wells and recharge this morning. Thank you. So, we'll talk about deep infiltration in dry wells. A little bit about me. I've been in the commercial development engineering industry for about 22 years. I worked for the city of Scottsdale for the first few, so I got a municipal side of things, and then mostly as a consultant and a developer after that. But almost always I've been dealing with dry wells because I'm from Arizona and that's what we do there. So a little bit about my company, and the reason I'm talking about this is we are kind of dry well experts. We've been doing this for 43 years and we've kind of got it dialed in. So we're an employee-owned company, started in '72 as a drilling company, got 3 offices, a big office in Phoenix, a smaller office in Bloomington, and we've got Travis Pacheco up here. He's sitting in front. The Bloomington office is growing very quickly right now, our Southern California operation. We're licensed in the West and Southwest, specialize in the design and installation of dry wells for stormwater infiltration. We only install and maintain drywell systems, and we're going to see a little bit about our MaxWell system, but it's a pretty generic look at it. So let's go forward. 80,000 systems we've done in the Southwest. So that's our expertise, that's our experience, and that's why we're here today talking to you about this. So a little bit about Stormwater 101. I think people know the impact of development. When you have, before you've built anything, you've got a little bit of runoff here, and then you add all your impervious surfaces. You've got buildings, parking lots, etc., concrete sidewalks. You're going to get a much higher peak runoff. So we can deal with that in a whole bunch of different ways, but 2 of the big ways are a detention system where we can try to take that same area under the white curve and try to mimic the pre-development peak, or retention, which is how we do things in Phoenix, and all the area under the curve gets stored on site and it never gets off. And that's where dry wells have to come in because the surface soils can't take that much water. So what that looks like functionally, before you've built anything, you've got about 50% of the water getting infiltrated, only 10% is running off. And after you urbanize or you develop, you basically have a reversal of those 2 numbers. Only 15% is going down and 55% is running off. And that's a big problem. So the additional runoff is causing problems, but also the lack of infiltration is another problem that causes us to want to store that water. So we're managing stormwater. The old way used to be to grade the site out to the street, let it go out in the street. Stormwater is moving into channels, creeks, or whatever, and it goes out sometimes to the ocean, sometimes to larger water bodies. That creates a lot of problems. You get downstream flooding, erosion, waterway impairments. So the new way is starting to move towards, I think people are familiar with LID, low impact development. We want to catch the rainfall on site where it lands, or at least some portion of it, keep it there, sometimes just until after the peak is gone, and then we can either let some of it go down and let some of it go off. But I think the big goal here is capture, treat, and infiltrate. And to the extent we can, we'd like to mimic pre-development hydrology so that we're still getting that 50% going down and only 10% going off. So up here, I think a lot of policies, MPDES permits, MRPs, et cetera, have a provision C3, and that's going to be talking about the different thresholds we have, size and percent impervious for new developments, redevelopment projects, special projects, roadway. And once you hit those thresholds, you've got a regulated project, and then we start looking at what's required for that. So almost always, infiltration is the first thing they want to see. They want to do infiltration first. After that, if you can't do infiltration and it becomes infeasible for a number of different reasons, we can go to harvest and use, evapotranspiration, and I think the last ditch is to do biofiltration and discharge it, let it go off-site. But for the purpose of today, we're going to talk about infiltration and focus primarily on that. Can everyone hear me okay? Okay, good. So why do we infiltrate? A couple of reasons, a bunch of reasons. Two big ones are drought storage. So droughts come and go. It's a cycle. You can see here it's moved across. It got not so bad, worse, very worse, and this year it's getting a little bit better. So in the wet years, and we do have wet years, although it's kind of hard to remember some of them, we could be taking that water and we could be putting it back in the ground and replenishing the aquifers, use the aquifer for a storage tank. So we'd like to do it that way to the extent we can because our demand is only going to go up. Another big reason is subsidence. Subsidence is a direct result of groundwater withdrawal. When you pump and pump and pump on an aquifer for years and not let any water get back down in the ground starts to subside. Well, this is the Central Valley, and you can see just from 1965 to 2013, they lost 7 feet of subsidence. And I think NASA is looking at this today with their satellites, and they're saying this area of the state is sinking at 1 or 2 inches a month. It's just kind of receding into the earth. So it's a pretty big deal. And to the extent we can start to rehydrate those clay layers, which are getting dried out and collapsing, we can't reverse that subsidence, but hopefully we could at least stem it and prevent it from getting too much worse. So now we're going to look at getting stormwater in the ground. So there's a couple different types of systems to do that. We'll look from shallow to deep. So these are some examples of some different shallow systems, and then the drywell is here on the right side. So shallow systems are really good for sites that have permeable soils, and I think people like to say A or B type soils near the surface. So if you've got that condition, and that happens from time to time, you're going to get pretty good infiltration near the surface using a shallow system. They're also good for storage. You can provide storage in the shallow system, and then the area beneath can be the infiltration part of it. They're really good with helping with earthwork because you're creating some fill. And then but systems like this, having a pretreatment component for these types of shallow systems is really critical because, again, they're relying on all the gravel that lies beneath, so you've got to keep sediment from getting in that because obviously you don't want to dig a system like this up if all that gravel gets impacted. Some shallow ways to do infiltration that are natural, bioswales, rain gardens, infiltration trenches. Amended soils are usually going to be used for a lot of this. This is probably the best example because all this grass can filter that stormwater as it's running through to remove the sediment and stuff before it gets to that white rock, because once that trench gets filled in with sediment, the only way to fix it is basically to dig it out and replace it. You can't clean it. So drywells. Deep infiltration. So here's some simple ones. Again, not a lot of pretreatment on these. They're really susceptible to sedimentation, and they can generally have a short life. And then we can have some more advanced drywells that are going to have some pretreatment here, pretreatment on this one. I think this is Barbara's Elk Grove drywell. Here's a Portland example. Pretreatment's happening here before it gets down into the drywell. And something here, pretreatment fills up and goes down in the ground. So pretreatment is the key, and we're going to see that a little bit more later. So very important, and that's what you're going to give you a long life and high performance. So looking at a drywell, if we want to use a drywell, there's a bunch of things we need to identify on the site. I think most of these will be borne out by a phase 1 study and a geotechnical evaluation. We'd like to know where groundwater is. Ideally, we want to stay 10 feet away from that. Proximity to water wells, where are the water wells in relation to your site, and that'll be identified on a phase 1 generally. What's the soil permeability? Again, identifying the types of soils that are down below, especially if you've got a confining layer. We want to know if we can find A and B type soils below, so we want to know where those are. We want to know if there's any contamination on the site. We want to stay away from that. And then any specific requirements, maybe there's buildings nearby, retaining walls, and we need to stay away from things like that. And then any geotechnical hazards, liquefaction, collapsible soils, we need to have those things identified, and that'll a lot of times be taken care of in a soils report for the project. So the role infiltration play, it helps with flood control, prevents downstream erosion if we're keeping some water on the site. We can mitigate the effects of hydromodification. We can help maintain the pre-development hydrology, and we can increase aquifer recharge. And then we choose a drywell to do the infiltration. We get the added benefit of being able to get past the upper confining layers, if there is one. Again, a very long service life, a very small footprint, and we can retrofit, especially some of those shallow systems. If they don't work any longer because they have gotten silted in or impacted, a drywell can be added to a system like that and make it work really well again, and use the shallow system more for just the storage part of it. Just something to note here, and this shows up on a couple slides. The drywell or the shallow systems, they're not doing any of the infiltrating. The soils are doing the infiltrating. So if you've got good soils below, the drywell or the other system is just providing a connection from the surface down to the good soils, and hopefully it's got some pre-treatment in it to prevent that from getting ruined over time. So let's look at some different studies here that have, drywells have been studied for decades. The first one, the EPA came out in 2001 with a final determination. I think this spun out of the lawsuit from the Chesapeake Bay. They studied drywells, class 5 drywells, and they found out that the absence of frequent, widespread, significant cases of actual contamination is good evidence that they have the low potential for to endanger. Class 5 drywells as a class or subclass do not pose an endangerment to underground sources of drinking water, since documented cases attributable to them are rare, and they did not show any evidence that class 5 wells as a class or subclass are contaminating underground sources of drinking water. That was a pretty definitive document that came out, and it was a really exhaustive study they did from coast to coast. It's available online. Let me say, anything that's in the slideshow today, I'm happy to provide to anybody who wants it. Feel free, I can send you PDFs of everything that's in here. This is a HydroSystems study. This was done in Chandler, 2010-11 timeframe. The whole reason for the study was to see how effective, it was our system that we had studied, how effective it was at pre-treating and getting water back in the ground. The site was about 24 acres. It was about 80% impervious, and there was one dual chamber drywell on the property. So it was 7 months long. There were 17 events. It rained 17 times, about 7.5 inches of rain. We got 92% average total suspended solids removal through our dual chambered system, and we were able to put 3.8 million gallons back in the ground just through one drywall, one rainy season on one piece of property. So those are pretty big numbers. And then effective mitigation of all pollutants. It's an analytical based study. Again, I'm happy to provide it, all the tables and charts showing the reductions from solids to other different constituents. So the quality, here's some conclusions. The quality of the stormwater process through the MaxWell exceeded expectations. This study supported the use of drywells for efficient treatment and recharge of stormwater in commercial areas, does not pose a significant threat to the underlying groundwater, and we were able to recharge 3.8 million gallons instead of let it run off to the Salt River. Excuse me. Another study that was done, geosystems analysis, was contracted by the city of Chandler. The whole purpose of this was to see how the city's stormwater policy affected groundwater recharge, and I'll just preface this by saying just about every city in Phoenix has a 100-year, 2-hour storage policy. So basically, when you develop, you've got to provide storage for about 8,000 cubic feet of water for every acre that you develop. So it's quite a bit of water, large basins, underground tanks, etc. So the city's policy was 100-year, 2-hour storage. So they wanted to see how that was affecting their groundwater, and it came out really well. So they figured out that before development, there was about 191 acre feet a year being recharged through an undeveloped piece of property. And then after development, because remember, 100-year, 2-hour storage, nothing's escaping smaller than a 100-year storm. So not like the slide we showed earlier where 55% is running off after you urbanize. Here, nothing is running off past the 100-year storm. So 2,610 acre feet a year was being put back in the ground. So that's a 1,200% increase. And the study went on to say the groundwater recharge from stormwater runoff and capture represented a potentially significant water resource for the city of Chandler. And I can tell you almost all the major aquifers in Phoenix over the last 40 years have remained relatively stable despite our population boom, and I think this report kind of really bears that out. The water augmentation study was done in Southern California. Who's familiar with this? Anybody? Huge project. It was 7 years long, and I think they're still continuing to monitor this to some degree. The reason was to see if it was safe and effective to infiltrate urban stormwater into the aquifer. So they estimated in this watershed, and you can see the watershed is kind of like right here. It's an enormous watershed of the San Gabriel and the Los Angeles rivers. They estimated about 578,000 acre feet a year through one rainy season was available for capture and recharge. They selected 6 sites, varied from a school all the way up to a metal recycling yard. And this is what the cover of the summary looks like. Really, really great document. So they did it for 7 years, and it was the results came out that infiltration and using stormwater infiltration was a really good, and again, analytical-based study. There's all kinds of charts and tables, just volumes and volumes. That's all available, and I'm happy to provide it or point you to it. So no apparent trends indicate stormwater infiltration will negatively impact groundwater. Suggested that the quality of the groundwater at the 6 sites was improved or stable for most constituents, and they surmised in the report that the groundwater was dirtier than the stormwater, so it was getting diluted. They said to do a decentralized approach for stormwater management, and again, that's the LID, where you capture some part of the rainfall on site and don't grade the site out into the street. And then soil appears to be very effective at removing TSS, total suspended solids, and bacteria out of the stormwater. So I just took a look at the Elk Grove study. I think Barbara's here. Her group kind of put this together a couple of years ago, and I think they're in there wrapping it up, and they're going to start presenting some details and some data soon. The whole reason for this one was to see if they could infiltrate stormwater without impacting groundwater and to help alleviate flooding. For the purposes of today, I'm just going to look at, they did an annotated bibliography of about 20 different studies that were done from coast to coast, and I'm just going to generally discuss some of the stuff that they found in their evaluation of those. And you can see here, all the way from New Jersey out to California, Hawaii. So they looked at these. The basic findings were drywalls don't appear to be contaminating groundwater. Using pretreatment is really key to helping a drywall function well and having it last a long time. Consider the use of drywalls on a site-by-site basis. I think that's important. Vadostone wells provide excellent filtration, all that soil we have before it gets to perk down. And then again, stormwater is a valuable resource. I think that's a common theme that the state has picked up on. So some of the stuff that spun out of this, and forgive me for all the reading, this is pretty much the end of the reading. So little evidence that stormwater was negatively impacting groundwater. Again, use pretreatment to minimize the likelihood of groundwater contamination and clogging of the dry well. Urban runoff to recharge groundwater is a practical option for expanding local water supplies, and then infiltrating runoff can make significant contributions to recharge, and then metals, again, were attenuated in the vadostone, all that filtration that's occurring with that separation. So one last one, the Central Coast just came out with this in 2015, Low Impact Development Initiative. Geosyntec looked at drywell BMPs. They provided recommendations in their report. It's kind of a memo. They're looking for statewide regulations, standardized BMP, drywall maintenance, recommendations for drywall maintenance. They highly recommend looking at the site in detail to figure out whether you should use drywalls on it. And then some drywall design requirements, and then ways to evaluate a site. And we're going to look at these last two here on the next couple slides. So they recommend, in terms of designing a drywall, we're only going to use, again, type A and B soils, well-drained soils. We're testing the site for infiltration at the depth you're proposing. So don't just do a shallow infiltration test and say, oh, clay soils, and walk away. If you want to use infiltration at a 50-foot drywall, then we should drill a hole to 50 feet and see what the soils are like down there. They recommended separations for groundwater, so I think it's a 10-foot minimum separation from the bottom of the facility to groundwater. I think they mentioned 100 feet away from a dry well, or from a water well, and then some specific distance away from other dry wells from each other. They want to have a 10-foot minimum penetration into a permeable strata like sand or gravel. Setbacks from slopes and foundations, avoid contamination, use common sense factors of safety, and then of course register them with the EPA when you're finished putting them in. So here they say dry wells are significantly greater stormwater runoff volume reductions and aquifer recharge. Dry wells enhance infiltration by penetrating clay and other less permeable layers that otherwise limit infiltration. And then combining biofiltration and dry wells can optimize resources. And then state level regulations and a standardized BMP are needed to give practitioners the proper guidance for siting and designing dry wells. So I think those are pretty big findings coming out of here. Some of the regulations we looked at just up here in Northern California, you can see on the left, we just looked at whether low impact development was in there and required or at least recommended. And all of them said promote infiltration first. And then a handful of them even had allowances to use dry wells in the language of these policies and these regulations. So again, there's quite a few places up here that already allow dry wells, or at least we'll look at them so we can go and do that. A number of cities, I just looked across the country, this is not exhaustive, have their own standard details for dry wells. Of course, Arizona, there's quite a few, but all the way back east in Connecticut, Oregon has quite a few, Washington State, where they use dry wells pretty regularly. So here's some different examples. Hesperia, Victorville, these are both kind of dual chambered systems. Los Angeles, if you walk in Los Angeles and you want to build a dry well, that's the detail they'll hand you. And you can see here they finish it. Usually it's a curb inlet in the sidewalk, and we'll see an example of that on a case study. Portland, Oregon, it's a two-part dry well, pre-treatment chamber here, and then the water goes over into the dry well on that side. Oregon, and then Palm Desert, California. So again, standard details are a good thing. It lets people know that they're available. So engineered dry wells, these are torrent resources. These are our MaxWells. We started in 1972 with our MaxWell 1. We're up to MaxWell 4 now, and then we have a MaxWell Plus, which is a dual chambered system, and we'll see coming up about that. So they are pre-treatment devices as well as infiltration devices. They're designed to get the water back in the ground as quickly and cleanly as possible. They could be site-specific. We can tailor them, especially in areas where we've been. We use our boring logs, and we can set the depths. Where we have experience, we generally don't rely too much on the geotechnical engineer's data. We have our own boring logs and depth information. So the design's engineered, and most of it is patented. And then the technique in which they're put in is pretty critical to how they function. So most of the people that are with us have been doing it for 15, 20, 30 years, and they can really get these things in quickly and make them work well. So some of the reasons why dry wells work good, again, I mentioned confining layers. Generally, we see some pretty consolidated, compacted material near the surface. Once you get down into the 25-foot range, you start to see better, looser, uncompacted material that will be free draining, alluvium, sand, etc. We get the benefit of a taller water column. Everybody knows if you swim to the bottom of a swimming pool, you feel pressure in your ears. That's the same pressure that helps our dry well work a lot better than a shallow system would. So for every foot of depth you go down, you get a little bit under a half a PSI. So for a 69, 70-foot dry well, there's an additional 30 pounds per square inch of water pressure just pushing that water down into the ground and out into the soils as quickly as it can go. It's a huge differentiator between a shallow system and a deep system. So that pressure increases the perk rate. Huge difference maker. So here, let's look at some engineered dry wells, and this is our MaxWell 4, our single chamber. But again, soils are doing the infiltrating, not our system. So a single chamber, these are ideal for large landscape areas where there's a little bit of overland flow. The water's got to flow overland before it goes in. Ideally, you'd use a bioswale or some sort of upstream pretreatment. We're getting big TSS removal. That anything that makes it through will get settled out in the chamber up to here and before it overflows. The screen and the shield on top will help keep anything that happens to be in the water from getting down into that white pipe, because that could clog up the system below. Floating hydrocarbons can be removed by this little square orange pillow in here. Each one can hold up to a gallon of product like gasoline, diesel, oil, grease, whatever might come in with the stormwater that doesn't get removed, that thing can help take out. Oops. And then the number of dry wells is generally going to be calculated depending on a number of factors like soil infiltration rate, depth to groundwater, and we can kind of back into a design and how deep it should be and how many you would need. Here is our MaxWell Plus system, or a dual chamber dry well. So basically what we just looked at was a single chamber on this side, but you can see here the lid is solid. All the water comes in this side, which is a primary chamber, and it needs to fill up and then spill across and down into the drywall chamber. So these are ideal for large impervious areas if you don't have a lot of landscape areas, because you got the extra pre-treatment on this side to trap out sediment and debris coming off a parking lot or something like that. This little filter, slotted filter right here, is only about 1/10 of an inch slot, so anything bigger than 1/10 of an inch is going to get left in the primary chamber and not make it across onto the drywall side. These can be used with or without bioswales or upstream BMPs. They work phenomenally well, and again, this is the one that was tested in our Chandler study that we did, and we got a 92% average removal of suspended solids through this system. We get the extra pre-treatment, stormwater is treated 2 times, and the same drill, number of drywalls is calculated on a number of different factors that we get in the design phase from the civil and the geotechnical engineer. So just to recap, when we're looking for drywalls, using drywalls, we'd like to know where groundwater is. Ideally, we could drill to 120 feet, so ideally groundwater is at 130 feet so we can get that 10-foot separation. The average depth of a drywall we've installed in the Southwest is probably about 80 feet. So most don't go to 120 feet. Some of them are put in as shallow as 20 feet, depending on the soils. So it just varies. We never want to put a drywall on the site where they're going to have hazardous materials stored or used. We're going to make sure we keep them separate from that. Ideally, we'd have some room on site for doing some upstream bioswale or some sort of treatment. A great thing to have for a drywall is a confining layer, because if you've got that, you need the drywall to get past it. Generous landscape area, no water wells in the vicinity, and ideally we don't want any contamination, plume or anything. We want to stay away from that completely because we don't want to spread it or make it worse. So we'll look at building an engineered drywall, drilling and building. So our rig, this is called a bucket rig. We have a number of these that will mobilize to a site. Generally takes 2 to 3 days to put in a drywall from the day we show up until the thing is ready for use, completely constructed. So the bucket here is 4 feet in diameter, and you can see it kind of going down into the ground. It's about 4 feet tall, so we're taking soil out of the ground at 4 feet at a time. It's about 2.5 yards of soil every time the bucket comes out to dump. So I mentioned 4 feet. You can see down here in the lower hole, the bucket's down there, but then the upper hole is a little bit bigger. So after the hole is drilled, say for instance we were going to install a 70-foot drywall, we would drill the 4-foot bucket all the way down to 70 feet. We take the bucket out, and they pop out a little arm on each side or just one side, and they'll send it down the same hole, and they'll basically ream out the upper hole to 6 feet in diameter. And I'll show you why we do that in a second, but you can see it clearly right here. So this upper hole, 6 feet, lower hole, 4 feet. So we need that because our chamber material needs to sit in there. So down here, the 2 dark lines are 4 feet apart, and the upper lines are 6 feet apart. So after we fill the gravel, we got to nest the chamber down in there, and then we fill around it with some gravel and concrete. So the first thing we do after the hole's drilled is we put a sock, that's that heavy black line, all the way down toward the bottom of the drywall. That's going to keep fine material from coming into our gravel pack and clogging it up. And also, if it moves from outside into our gravel, it could create some softness, and we'd have subsidence coming down the side of the drywall. So we want to prevent those things, and the sock does that nicely. Then we have our flexible pipe that we cut that to length. There's an 8-foot tall slotted well screen that we buy from the factory. That's about it's all 6-inch diameter. So they'll lower that. They kind of suspend it off the chain right here, and they'll lower it down into the hole. And you can kind of see there's a T right there and a chain hanging down into the drywall, and we'll see that clearly right here. So the bottom of that screen pipe is at about 1 foot off the bottom of the overall excavation, and then we'll start dumping rock in the hole, which is the gravel drain field. It's about 3/4 to 1 inch clean wash gravel that has very, very little fine material in it. So it's 30 to 40% void space in it, so there's quite a bit of storage just in the gravel pack. And then we put the liner down in the hole. So the liner gets placed in. The first piece that gets put in is perforated, so that after the storm's gone, there's a way for the water to get out into the gravel on the sides and not stay full, which could create vector control issues. If we're going to put a drywall in pavement, which we do regularly, We would leave our framing grate loose, so whoever comes in last can put it right where they want it with shims and get it to fit in the pavement or the concrete just right. If we're going to be in a landscaped basin, we generally want the grate up about 2 to 3 tenths above the design grade in the bottom just to prevent the last bit of stormwater from kind of dragging all the really nasty water into the dry well. We want that to settle out through the bottom. So once we've constructed the both chambers, we just trench across with a backhoe to put our crossover pipe in there, and you can see it sitting right there. Again, there's the slotted pipe in the dry well primary chamber. So it's got slots in it, again, 1/10 of an inch only, so anything bigger than 1/10 of an inch, that solid's going to get left on the primary side. We patch up all the penetrations we've made with some non-shrink grout and keep it from anything coming in. So this is the primary chamber side, so as water comes down in here, it fills up, goes through the slots, and it goes this way, and this is the dry well side, so it will pour out here and start to go down in the ground through the dry well. When we're done, we use a 2-sack slurry to fill in all the trench near the surface all the way up to subgrade to prevent some sidents and lock everything in place. And then we usually put fabric on top of our grate because we're out there very early in the process. Usually right after rough grading is done, we show up. So there's still months and months of construction going on. We want to keep that construction stormwater out of our dry well while the site is being finished. I'm going to play this little video. Okay, thank you. So this is just an animation that kind of shows how our system operates. So you can see the pillow floats. So as water flows in, it stays on the surface. Those are that slotted pipe. Water moves over. And if something does get through, there's a little bit more storage volume for sediment and debris on this side that it can settle out before it goes down. So you'll see right here, this is going to be like a little split away. So the only way water gets in this pipe is through that little annular space right there. It goes down into the ground. So ideally, everything up here is consolidated and doesn't drain, and this is where all the good soils are down here. And lets it out. Cool? That's a good question. We've never had to replace one. She asked how long till we have to replace the pillows. We've never had to replace one because it got full. They start to get black around the edges just from the little bit that comes off of a parking lot. But generally they get vectored out. Once the beads or once the pillow gets activated or used, it becomes inert, so it's not even hazardous. And we'll vector it out with the cleaning, with all the sediment, trash, and debris, and it just goes in the landfill, and we throw a new one down the hole and move on. Whoops. So here's just a kind of a visual database of our installations. This is Southern California. This represents about 15,000 drywell installations, anywhere from the most we've ever done in Southern California is 30 drywells on one project. So 1 to 30. It's about 15,000 dry wells, and obviously we've been in Arizona for quite a bit longer, and over there we're treating and disposing a lot more stormwater. So that's 65,000 dry wells right there. Very well covered. They're the go-to. Dry wells are required for pretty much every municipality in Phoenix. Some different examples, typical applications, big grassy retention basin. There's a number of dry wells in the bottom of this. Of course we can't see them because it's so far away. So commercial office buildings, large industrial warehouses. Again, the green space around here, little moat-style retention areas. Dry wells just go in the bottom of those. Big grassy play areas. A lot of times you'll see dry wells in the bottom of a retention basin where there's a pocket park for a residential neighborhood. We just did a couple of these in Southern California near our office. Here's a public park. So we can even, let me point out, a system like this, or this, where there's a lot of grass, maintenance on something like this for our systems is generally 7 to 10 years between maintenance cycles because of all that grass. Does a really, really great job of filtering. You can get a system like this, though, where the drywell's sitting up front here. This thing may need maintenance every year with all that litter and debris and leaf drop. So we let people know when we're done, hey, listen, this might need maintenance more frequently. It's an HOA. They can keep an eye on it. Usually once the drywell If it's a plus system, once the debris starts to get up toward the bottom of that screen, we want to get it sucked out before it starts to impact the slots. Here's another one. This is a good example of seeing sticking up about 2 to 3 tenths above the bottom of the basin. That's ideal. It's a brand new installation. Here we can put it with underground storage. This is a very typical application for Phoenix, and we're starting to see this more and more in Southern California, where we've got large diameter corrugated metal tanks that are going in to provide the stormwater storage volume, and then the water's got to come out of there, and you can see that tailpipe right there. That'll be connected over, and that's a primary chamber. So there's about 6 feet of more chamber below the ground surface right here. That's going to provide that sump for anything that's left in the stormwater to be captured out before it moves over into the well. The pipe, yes. Yeah, and again, she just asked about the storage tank and how it operates. That's very standard for Phoenix. Southern California, a lot smaller volumes of water, but they are using that more and more. Sometimes they're using plastic like 60-inch diameter. We see that now in Phoenix, 8, 10, 12-foot diameter pipe, huge tanks. So, and we can accommodate. You can kind of see the section right there. The water gets in and it goes across and then down. Another application, this was in Glen Oaks Boulevard in Los Angeles. Every time it rained, this intersection was underwater for days. City of LA asked us to come in there. We put 5 drywells in this intersection. The first one right here, you can see this pork chop traffic diverter. They put a curb inlet right here, and they put a pipe across. There's a primary chamber there, and then they put a drywall on either side, and it's all finished in the sidewalk. So you can actually see the pork chop, the back of it. There's the saw cut, primary chamber, and then drywell. And here's the front way it looks. So these did a great job. They're capturing up to 9.3 million gallons a year just from this intersection through 5 drywells. And then across the street, right over here, there's another drywell. So this one is a curb inlet right here. It goes to the primary chamber. And then in between, the City of LA asked us to put a meter. So we put the vault, a meter vault right here, and then the drywells right here. So that's the meter in the meter vault, and it's just a flip-up cap right here. They can go take a direct meeting, and they just assume that all the drywells are working the same, and they can read it once a year or through the rainy season and track how much recharge is occurring. And it's really helped the flooding quite a bit. Another one, this was just a couple months ago, very similar, and again, City of LA design. So curb inlet, primary chamber, drywall chamber, and you can see that right here. This was a Green Street project down in Sun Valley. There's lots of stuff on the internet about this. We put in 46 drywalls on a 1-mile stretch of street, and even some of the streets that are up the hill, so the water comes down, and before it gets into the street, it's being captured out of the curb. It's been pretty successful, and it's Branford Street in Sun Valley. So all the drywalls are kind of right along here, and you can see it right there completed. That's the curb inlet. It goes into here, goes into the primary chamber where it has a chance to settle, and then goes down into the ground in the drywall. I think they're only 35 feet deep because it's really, really sandy material here, and they're taking tons and tons of water. The City of LA is going to share, DWP is going to share with us some data. They've got some sensors in a number of these wells, and they're going to share with some data with us pretty soon. Some other things we do in Southern California, this is Olympic and Olive in downtown LA area. We're putting drywalls under buildings. So 2nd, 3rd story below grade parking. Before they build anything, we get down there. Our drill rig's in the basement. You can see that's the lowest grade, and the street level's up here. So we've got, usually these are 100% impervious projects. They've taken up back a sidewalk to back a sidewalk. All the roof water gets piped down to the basement into a vault. Vault's connected to our drywell, and it goes down into the ground right here. So we've done that on all 5 of these projects now, and a number of others as well. So talk about the confining layer. San Diego project, this was our first San Diego project, January of last year. The initial, it was on UCSD's campus. You could see here how clay the soils are. This is the excavation for the underground storage system. This was a parking garage project. So all the water coming off the parking garage was going to be captured and infiltrated through a shallow system, but they figured out really quickly after they did the perk test that the shallow soils were not going to take any water at all. So we hired a local driller just with a geotech rig to go out, and they drilled a 70-foot hole for us, and they did a perk test down the hole, and then they had 160 inches per hour of infiltration rate through that hole. So obviously the drywells were going to work. We put 2 of them on the site, and they worked so well that the civil engineer was able to reduce the overall amount of storage that they provided to a 50-year volume instead of a 100-year volume, and I believe the difference in cost more than paid for the 2 dry wells. And I think it was about 0.28 cubic feet per second through the dry wells, which is like 130 gallons a minute sustained flow rate. And then these both dry wells had an overflow out to the city street in case the capacity of the dry well couldn't keep up with a larger storm. It would safely overflow to the street. And we're doing a number of additional dry wells on sites nearby this one. So our maintenance here, very simple. It's a Vactor truck. You can see our Vactor truck right there. We've got 5 of these. It just basically remove the lid, loosen up the sediment that's collected, Vactor it out, and take it off to the landfill. Longevity, 99% of the dry wells that we've installed, Torrance installed over the last 43 years, are still in operation. So the pre-treatment is the key. It allows us to trap out the sediment and keep it out of the gravel pack, and these things last basically indefinitely. We've not seen any get ruined. So here's some conclusions. Just dry wells, again, after all the studies we've seen, our experience, very minimal risk of aquifer contamination. We can get past the confining layer. We're recharging the aquifer with all that storm water. Dry wells can have a long service life if they're designed properly. A very small footprint, relatively low cost, fast. Again, we can be in and out in 3 days per system. I think that's pretty extraordinary. Simple to maintain, and we can do them in a flow-based or a volume-based design. Phoenix, it's 100% flow or volume-based. Those dry wells that we put in Los Angeles are all volume or flow-based. Excuse me, all flow-based designs where they're trapping off the first flush or some of the peak flows and putting them down, and then everything else gets to bypass. So let's see, water's precious. This was interesting to me. Of all the water on the earth, 95.5% is salt water, and only 4.5% is fresh. And most of that is tied up in the ice cap and the swamps. So there's less than 0.1% of the water available on the earth for reuse, for us to use that's readily there and enabled. So I think we owe it to ourselves to really manage it properly and not let it run out into the ocean. Yeah? Desalinization?
Yeah. What are your thoughts on desalinization?
Yeah, I think it's extraordinarily expensive. I think it takes a long time to get permitted, and I think, I don't know personally, I've heard it's extraordinarily heavy on greenhouse gases and energy consumption to produce the water, and of course then there's the byproduct of the really salty water that they have to dispose of. So I don't know, I guess it depends on your position. There's an article by Water in the West, I think the next slide talks about it, and I think, well, I'll just get to that. There's 3 ways to have a sustainable water source. Desal is one of them, because if you can get the salt out, we can use that. The other thing is to have increase the capacity of our reservoirs. So this article, Water in the West, talked about increasing the capacity of reservoirs, which is only about 50 million acre feet of water currently. So to increase capacity, you need to get permitting, construction, and raise the walls on these dams and get more and more. And they just talked about the storage in our aquifers is between 850 and 1.3 billion acre feet of available space to be taken up by future recharge. So it's pretty powerful. And they also talked about the cost of recharge versus construction for dams and then desal. And I think the construction of dams and increasing reservoir capacity was about 5 times more expensive per acre foot than just putting water in the ground, and 7 times more expensive for desal. So I think when you look at aquifer storage, the capacity of the aquifers is huge. The water won't evaporate like it would out of a reservoir or a dam. It improves the ecosystem because you're getting water back to help replenish groundwater flows and streams and underground hydrology. The permitting is very minimal compared to what it would take to do a reservoir or a desal. And then low impact to the environment, and then low cost, obviously, again, 5 times and 7 times more expensive. Go ahead.
So in what instances would you say a desalinization plant would be preferred over an aquifer storage?
It's probably a site-by-site basis. I know they just built the one in Carlsbad. I'm guessing groundwater around there is maybe shallower since you're near the coast. Again, I don't know for sure. I know we've done a bunch in San Diego, but they're up on the bluffs and stuff. So it's a site-by-site basis. Depends on how badly you need it. But I think that one took like a decade to get permitted and constructed. So I mean, you can build recharge wells and you can build hundreds of recharge wells in months. And the permitting is pretty minimal. The cost is extraordinarily minimal compared to something like that. So I don't know. I think you do what you have to do. Obviously, there's a desal lobby, and they would like to see more of that stuff go in. So I don't know. I like recharge through dry wells personally.
Can you go through some, one of your early slides listed the need for standards, design standards, regulation to create consistency. So can you describe some of the regulatory uncertainty or kind of the permitting difficulties that people encounter? I mean, I assume that's...
Yeah. No, I think that's a good question. I think up here, Barbara did go through some permitting to get their Elk Grove wells put in, but in Southern California and Arizona, there is no permitting process other than the drywall gets shown on the civil drawings, it gets reviewed and approved through the plan review process, and it goes in. And then we register the drywell with the EPA, or in Arizona, we register it with ADEQ, Arizona Department of Environmental Quality, but there's no permitting per se. That's like a big onerous process. Orange County has inserted themselves into the process. We've started doing drywells there, but it's purely administrative. They want to see where it's going to be. They want to charge us $150, I think, for the drywall permit, and then when we're through, we have to submit to them like a drywall completion report, and then they close out the file. But again, purely administrative. There's no citing of regulation or policy. They just want to look at it, know where it is, and then, of course, with the closure or with the completion report, we send in the EPA registration. Yeah, sure. He asked about the environment, or siting a drywell and locating it. So the investigation, we'd love to know proximity to water wells. A lot of places in Phoenix say 100 feet. Barbara and I just chatted about this. She'd rather see like 500 feet. It just depends on what the comfort level of the administrating agency is. So 10-foot separation from groundwater is pretty standard. I think Portland says 5 feet. No contamination. We want to make sure, again, most sites that get developed, they're going to have a phase 1 environmental report, so that would locate some contamination. We never want to put a dry well near contamination. If there's geologic hazards like collapsible soils, we need to be careful of that. And when we build dry wells under buildings, there's a lot more than a standard installation that goes in. We're coordinating closely with the geotech and the structural engineer to make sure we're doing the right things to not compromise the structure. Let's see, separation from drywall to drywall, usually 50 feet minimum. A lot of cities in Arizona recommend 100, but they're flexible. 10 feet away minimum from a structure. And then 10 feet before we let water out, even if it's 10 feet away, we want to make sure no water is going to come out within 10 feet of the lowest structural member, like a footing. I'd be happy to provide a ton of regulations that we have in Phoenix and even some in Southern California as a go-by. I know we've been working pretty closely with Geosyntec, who's writing Orange County policy right now, and I provided to them about 8 different sets of drywall policies from the Phoenix cities, Gilbert, Chandler, Phoenix, Gilbert, Chandler, Buckeye, Goodyear. They all have a laundry list of things that you're supposed to do to get the drywall done the right way. Did that answer your question? Okay. Huh?
I just thought I might add a few things, if that's okay.
Of course, Barbara.
Jim, in response to the question you asked, as part of our drywell study in Elk Grove, we've looked carefully at drywell programs around the country, and especially focused on our neighbors to the north, Oregon and Washington. And some of Jim mentioned, I thought 500 foot was a good idea. It's not my idea.
Okay.
That's what the standard that they use in Oregon and Washington is. 500 foot separation from a public supply well, and I think it is 100 foot from like a domestic drinking well. where they'll site a drywall. They also have and I'm referring now to Oregon and Washington, and I've summarized, we have summarized this in a nice table. If anybody wants it, I'd be happy to send it to you. Oregon and Washington requires, the state of Oregon, but not Washington, requires monitoring to be done twice for the first year the drywall is in, and then yearly thereafter, unless you have like the city of Portland has an elaborate monitoring program where they go out 6 times a year and sample many, many drywells for a common set of contaminants. In terms of the siding issue, 5 or 10 foot of separation, like you already had mentioned. They don't allow dry wells to be sited where there's a risk of spill, like near gas stations, near places where vehicles are washed, like bus washing stations or vehicle washing areas where you get a lot of junk coming off the bottom of the vehicles. So they have restrictions in terms of if they're high-risk areas, they will discourage or in some cases prohibit installation of drywell. So those are just a couple other things that, in terms of the siting. And they also, some of the states will also require pretreatment. They wouldn't allow some of the single chamber drywell to go in without some kind of treatment.
I have a stupid question. I'm Lee. I'm with Caltrans. So drywell. Okay, so this probably wouldn't work like here in Sacramento. When they build the buildings downtown and they had to just dewater everything.
Right.
So okay,
Yeah.
so what's the depth of the groundwater where your system would start working?
A depth of groundwater is probably 30 feet because we can put in a 20-foot system, a 10-foot chamber, 10 feet of gravel, and that's about the shallowest ideally we would do, so we could still get our 10-foot separation. Yeah.
I guess my question related to that is groundwater fluctuates. I mean, most of the time
Yeah.
lately we see it increasing in depth or decreasing in elevation, but occasionally it rises. Have you ever come across a situation where?
Some of the cities in Southern California will say historic groundwater, like or seasonal high. So if it's up and down through seasons, and a lot of times geotechnical reports will identify that.
Okay.
And they're required to, depending on the requirements of the city, and they have checklists of what they have to provide. So I think LA County, you have to use seasonal high groundwater.
Then this goes back to a comment Barbara made about monitoring. Are you referring to monitoring of the stormwater flowing in? Are you talking about monitoring once it goes through treatment, or are you talking about groundwater monitoring? And does anybody ever require the installation of monitoring wells to better understand what's happening at the water table? Either of you.
Yeah. I'm going to leave Barbara to that because
In Oregon, but not in Washington, they require monitoring, and their standard is monitoring the water after runoff, after pretreatment, just as it's entering the dry well. And their criteria generally that they use is if the concentration of whatever the contaminant might be is lower than the MCL, maximum contaminant level, it's considered acceptable. Now, more recently, they've done modeling, beta zone modeling, and they found that, in fact, because of the attenuation in the beta zone is so great in some places when they have a lot of clay soils down below, that they have allowed, in some cases, for the concentration to be even higher than the MCL because they don't see any movement over long periods of time. But generally, it's the MCL for water as it enters the dry well.
Thanks, Barbara.
Just as a follow-up to that, I'm curious about what about contaminants that don't have MCLs?
But they
Barbara, I have a question. So does Oregon monitor public dry wells that are like in the street, or are they also monitoring private development dry wells like on a commercial office building project, or is it mostly the public ones?
both. The public wells are part of a program that is a 6 times a year monitoring of 30 wells on a rotating basis. A private well has a much lower standard because the risk is assumed to be less if you just have 1 or 2 wells, and that's twice a year, the year it gets installed, and then once a year, every year thereafter. And the reports go to the Department of Environmental Quality in Oregon.
Yeah, we've not done that at all in Phoenix. For 43 years, we don't monitor anything. And our groundwater has not been impacted, otherwise it would have come up.
Can you describe in a little more detail the maintenance? Is it literally just a vacuum truck going around?
Yeah. Remove the grate. Each truck has a jet rod to loosen this. That sediment almost becomes like concrete in the bottom because it's settled through water over time. They break it up and they have a 6-inch Vector hose that gets sucked out. Usually you could do 2 to 3 a day, and they just dump it at the liquid waste landfill. Super simple. Sometimes the screen gets a little gummed up, but they just hose it off with the jet.
So I have a question online about that. It says, how does the drywall screen of 1/10 inch in the primary chamber keep from clogging?
Yeah, it just doesn't. It gets some debris on it, but the water flows enough. And when they do maintain it, they use the jet hose to spray it off. Every once in a while, they'll be replaced. We're under development right now with a new device that will help keep that clean. It's like a little vortex spinner that will direct the incoming water down across that and prevent it from ever getting dirty. So that's something we're probably going to introduce this later half of this year.
Do we want to continue on with questions, or do you want to finish the slide?
I'm ta-da! Yep.
Actually, why don't you go ahead and finish because I have a couple.
Okay, go ahead. So just our conclusion, stormwater, again, valuable resource. That's a theme today. Infiltration, recharge, very beneficial. We definitely want to investigate each site, a site-by-site basis to decide whether a dry well would be effective on that site. We want to incorporate pretreatment, whether that be a primary chamber or an upstream bioswale, something to treat the water, get the sediment and any contaminants out to the maximum extent we can. Some guidance is needed from probably the state, some overarching agency to give people that are scratching their head on how to do it. And then to look to others. Again, in Arizona, we've been doing dry wells for 40 years. I mean, we've got it pretty well dialed in. We haven't had any contamination issues. Our aquifer's in phenomenally good shape in terms of volumes. So, I mean, we know how to do it. And again, 20 plus years in Southern California, and to my knowledge, they haven't had any issues or problems with groundwater contamination, et cetera, at least not through any dry wells that we've installed or been a part of. So that's it. Ta-da! Questions?
Yeah, I'll jump in here, I guess. A couple. The first one's more has to do with the costs and the O&M costs, and are those ongoing? So if you're going to put this thing in for 50 years, is it an annual cost that way, or is it's not really covered in the initial construction, I would think, right?
It's not, no. So a dry well, a single chamber dry well is about $30,000 installed, complete. Varies. I mean, it might be a little more if it's deeper, but most of the cost is in the upper 20, 30 feet. And then if we had to go deeper, I mean, it's just drill time and a little bit more rock and pipe. So it doesn't cost too much to go from 80 to 100 feet. It's a little bit of money. Maintenance or a dual chamber dry well is probably about $36,000, $37,000. So yeah, 28 and 38 is what we say. And then the maintenance, $1,500. Average maintenance is 3 to 5 years between maintenance periods, so they last a pretty good long time. That chamber can hold quite a bit of material before it needs to be cleaned out. And then if you've got a big grassy basin or something, again, 7-10 years between maintenance cycles. So a lot of HOAs in Arizona have these on their site, and they just budget for it in their annual budgets. And if they have 20, they'll get 5 cleaned, and then or 4 cleaned, 4 cleaned for on a rotating basis.
Good, thanks. One other question is more, I think I know the answer to it, but it's something more consideration I was thinking about as you're going through things. Has anyone done any studies just on the physics of the situation or the process, particularly in the vadose zone? Because over time, if for different climates, I see, say in Arizona, a lot of the recharge is going to be during storm events, probably during the summer. But in different climates, you may have a much longer duration of storms or a storm event in the winter, like here on the West Coast, particularly in the northern part of California.
Yeah.
Has anybody studied the vadose zone to see the differences in by artificially saturating the vadose zone for possibly prolonged periods of time, what effects that might have on the system? Because normally the water would infiltrate a lot slower, a lot less of a dump of water into the system. I could see issues, particularly in shallower situations where that you're saturating the system for a much more prolonged time period. Because there's just a lot more water going into
Yeah.
it on a prolonged system. Do you know if anybody's looked at that at all through monitoring programs or something like that?
Not that I know of. I know Emily's here. She's a grad student. She's studying some things, but I don't know if it's that specifically. I think she's studying more contaminant removals through the vadose zone, not necessarily performance of how water moves through the vadose zone. For me, and what I know about it, I mean, the more permeable the material, the steeper how it's going to go down, and the siltier and clayier, it's going to be a much flatter spreading out of the water, mounding. But not that I know of anyone's ever studied like the performance of the soil, how the water moves through it.
Yeah, that's one of the things we look at when we design injection systems, not in this context,
Yeah.
but another is where's the water potentially going to move?
Sure.
Particularly if you have a deeper confining layer below what you've drilled to look at, is that water going to stack up? If there's a huge amount of water being put in the system prolonged,
And create a
you may not
perch.
know where the water goes. It may not all go directly down.
Sure. Now, and again, to my knowledge, I don't know if anyone's actually studied something like that. We also build injection wells. I didn't discuss it today, and we've not done any in California, but we've done hundreds in Arizona. We did the Scottsdale Water Campus. Much different design than a dry well.
Yeah, I spent half my life in Arizona. We had like flash floods and stuff. So, I guess it's just because of in the Phoenix area, everything's all concreted over, that there really isn't like an environmental concern, because now the water's going back down into the system instead of just, now with the concrete, it doesn't have a chance to filtrate in.
Well, we're also collecting it though. I mean,
And so here's my stupid question, because I missed the first part of the lecture and I apologize. So the whole purpose why people are doing it, it's not because they're just mitigating some sort of environmental concern. They're doing it to recharge their aquifer.
well, the reason we first started doing this in Phoenix 40 years ago, City of Phoenix was the first city to have 100-year, we don't have a very developed storm drain in Phoenix system. So we had to do something with the water when the population boom and all the development was happening. So they had to do something with the water. So they created this 100-year, 2-hour retention policy. And that's a massive amount of water. So they figured out after the first few years of that the surface soils, the basin is nice and new. It works after the first few storms. The water will go down through the floor of the basin. But soon after that, it gets silted up with all that really fine material, and then it's like a bathtub.
And then you have the flashlight.
And then you need the drywells to get rid of it. So the drywells became a really quick necessity to drain those basins, because we also have to dispose of all the water that accumulates within 36 hours, all the way up to and including the design volume, which is just a massive amount of water. So you've got I think most places around here are 48 hours, Southern California 48 hours, some are 72 hours, and that's a vector control issue, as well as you got to make sure that the facilities are empty in case you get back-to-back storms.
So they're not measuring like that they're recharging aquifers or anything like that?
I think back then they were doing it primarily as a flood control and an erosion control measure, and I don't think they consider the aquifer recharge, but I think they consider it now. Like Chandler studied it, and over here I think that's the biggest thing is the aquifer recharge, and the fact that it also does flood control and erosion control is a byproduct. But back then it was the other way around. Yeah. Here's a question.
I just wanted to feedback to the question on desalination. The San Diego County relies about 90% on imported water, in part because the groundwater basins there are not suitable for a massive water supply.
Consumption, okay.
And in fact, there's very little artificial recharge, even of with major stormwater infiltration basins or imported water infiltration basins, as there are in Orange and Los Angeles counties. So desalination made more sense there, and dry wells may have more of a water quality flood control
Right.
benefit in San Diego County than it would be for recharging the basins as a water supply.
Okay, and that makes sense. It totally makes sense. Yeah. No, I said it's a case-by-case basis. You can do what you need in that area.
How about we ask some from online? So I have a couple questions, and I'm just going to read them. Can you discuss the potential infiltration via dry wells for California's industrial sites? Many businesses are struggling with compliance with the new industrial general permit, and water infiltration should be sometimes be a viable option. He also asks, what are the regulatory hurdles and permitting in California for industrial sites?
In terms of dry wells. Okay. In terms of industrial sites, do they mean like a warehouse industrial, or more of like an industrial use that's going to have potential chemicals and stuff?
Anything under the industrial permit.
Okay.
When infiltration's viable.
Yeah.
It's not always.
I guess on a site like that, you would probably have to design it to segregate stormwater away, just from a design standpoint, keep anything that's going to be containing or storing hazardous materials or chemicals separate, and maybe that gets treated and discharged, and maybe all the rooftops are designed to go to a basin where they're never going to have the potential to come into contact with hazardous materials. There's another system that we use quite a bit in Arizona called an Envibro system that we use on gas stations, and it has a whole extra component in it that has the same beads that are inside of the pillows. There's some bead pack filtration that would stop a flow if there was a catastrophic spill of a tanker. This thing would prevent water from getting into the ground. I didn't discuss that today, but we don't do them over here, and there hasn't even been a demand. But we do them, and the flow rates through those are generally a little bit slower than a typical dry well. And I don't know much about what's in the industrial permit for California. I apologize. But everything in Arizona, no matter what project it is, it gets a dry well. So gas stations require, from a regulatory standpoint, there's an aquifer protection permit that needs to be obtained from Arizona Department of Environmental Quality. So there is a little bit of permitting just for the Envibro systems, but a general dry well, we put that on a distribution warehouse like I showed earlier. I don't know, all those types of big box projects, but we call those industrial, but I think you're talking more about something that's going to be dealing with hazmat. So I don't know the answer to that other than to design the site in such a way to keep the water segregated.
There's a few questions on monitoring. What parameters, and I think you covered a lot of this, and there are some documents or reports that we can share. But in general, how's monitoring perform? Are the monitoring wells penetrating the infiltration zone, or is it water sampling directly into the secondary chamber? Both, or?
Yeah, monitoring as the big picture umbrella thing, we don't do as a rule in Arizona or even Southern California, like install a system and have ongoing monitoring. No. We've done studies which included monitoring wells, and for instance, the Chandler study, they were pulling samples from the influent stormwater before it was getting into the first chamber. They were pulling samples from the bottom of the pipe that's in the drywell chamber before it got out of the gravel pack, and then there were some monitoring wells that were, I think, 5 feet away and 10 feet deeper and a little bit further and yet even deeper to catch the water, and they were able to measure the flow. So they were pulling samples at 4 different points and comparing removal results through the analytical reporting. But in terms of ongoing monitoring, like they do in Portland, we haven't gotten involved in that, and we haven't needed to get involved in that.
How do you prevent the bucket drill from smearing soil material along the well wall to keep it from reducing the permeability through the sidewall of the well, or is this an issue?
We haven't seen it as an issue, and I know our maintenance or our mechanics, they put little weld dots all over the outside of our bucket to create kind of a roughness. So the smearing hasn't been an issue for us. Performance. And in Arizona, we test most of our wells when they're completed. We'll do a constant head percolation test on the completed well, and we're seeing rates anywhere from like 0.05 cubic feet per second up to like over 1 cubic feet per second. So again, I don't think that's been a problem for us historically.
And then I have a question on the sock. It says, does the sock have an opening at the bottom of the dry well?
Yes.
Okay. And do you have any, they say the reason I ask is we typically discourage the use of geotechnical fabrics in locations where one is trying to promote infiltration because of the risk of clogging. Is that an issue or?
Again, we haven't seen it as an issue. We have seen subsidence as an issue, which is why we use the sock.
Are there more questions in the room?
So like I mentioned before, if anybody wants any of the stuff that I've discussed today, I have PDFs of everything in here, including I can provide a PDF of the whole study or the whole presentation itself. I'd be happy to send it over. Thank you. Oh.
Thank you. And I also wanted to say, my name's Chris Began. I'm with the Stormwater Planning Unit. If anybody has ideas for future seminars, we're looking forward to getting ideas for additional seminars. I think this is the fourth seminar. And do we have any others on the books? Any? Okay. Anyway, we're looking for ideas. The other thing I wanted to say is one of the projects, one of the goals of the stormwater strategy was to incentivize, foster stormwater capture and use. So dry wells is something that we'll strongly support the use of in future water board documents. One idea that came up today that you've all heard about is developing standards. So that's one thing we'll be thinking about in the future. If you're interested in stormwater capture and use, my name's Chris Began, and I'm the contact for that project. So get a hold of me, and I'll keep you informed of all the things we're doing in the future. That project, probably I'll kick that off in about a month. I just got a contract executed that'll help me move forward with that. So with that, I want to thank Torrent for coming out, and thank you all for attending. For those of you that are attending on the web, thank you. I hope this was helpful and informative. And yes, that's it.
Good. Thanks, Chris.
Thank you all.
Good. Thank you.